Okay, the next problem in Chapter 12 is sample problem 12.2, applying the Clausius-Clapeyron equation. And I know this equation can look kind of scary. It looks just like there's natural log terms. Looks like there's a lot to it. But keep in mind that this is just a problem that basically has 1, 2, 3, 4 variable terms, 2 different pressures and 2 different temperatures, gas constant, and then another constant. Again, this is the enthalpy of vaporization. So when you see a problem that would need this equation, look for things that basically give you 3 out of the 4 variables. That's generally how you're going to see this problem. You'll see 2 different pressures and or 2 different temperatures of a substance. Or it might be a substance that they figure out what the enthalpy of vaporization is because they use 2 different temperatures, measure the pressure of a gas at those 2 different temperatures, and then solve for this unknown. So I guess I should say it's possible that you might have a problem where this becomes the unknown. So if we consider 1, 2, 3, 4, 5 pieces of information, using this equation, you'll always have one that you're solving for. Now, solving for one versus the other may be a little bit more straightforward than others. This problem tells us the vapor pressure of ethanol is 115 torr at 34.9 degrees Celsius. They tell us what the enthalpy of vaporization is, 40.5 kilojoules per mole. And so we'd like to calculate the temperature when the vapor pressure is 360 torr. So again, they give us 2 pressures, 1 temperature, and the enthalpy of vaporization. So we're solving for another temperature. Because there's a lot of information that's basically just in 2 sentences here, I find it helpful to kind of write down that information so that I can clearly see what I'm looking for. So we've got a P2, a P1, a delta H of vaporization, a T2, a T1, and an R. Those are the 6 different pieces of this equation. So let's see which ones we have and then which one we need to solve for. A classic mistake that students make with this kind of a problem is they don't match up the P with the correct T. And that's really important because if you were to switch these, if you put, for example, they give us 115 torr and 34.9, if you called P2 115 and you called T1 34.9, you're going to get the incorrect answer. So again, writing this out here allows me to try to minimize that mistake. And whether you call the higher or the lower pressure P1 or P2, that really doesn't matter. So in this case, I'm going to call P2, since that's the second pressure that we're going to, 760 torr. P1 will be the initial, so I'm going to call that 115 torr. The delta H of vaporization is the constant given as 40.5 kilojoules per mole. T2, again, that's what we're trying to solve for, right? We'd like to know what the temperature is when we're at this second vapor pressure. So this is going to be our unknown. Our first temperature, again, is going to be 34.9 degrees C, and then our R constant is 8.314 joules per mole Kelvin. Again, a classic mistake sometimes that students will make is they'll try to use the 0.08206 number for this, but that is going to have units of liter atmosphere per mole Kelvin, and that won't match up kind of with what we're having here. So in this case, we have to make sure we use the right R constant. Having units when we write these down is really important because that also allows us to see that our R value has units of joules per mole Kelvin, but our enthalpy has units of kilojoules per mole. So in order to make sure that our units work out correctly here, you either have to convert your R value into a very small number, or I think it's easier to convert this delta H of vaporization into a larger number by multiplying by 1,000. And make sure that you're good with kind of making those unit of 1,000 conversions, that you understand to go from a larger unit like kilojoules to a smaller unit like joules. That's going to require you to actually multiply by 1,000. Okay, so what we're going to do now is just put all of these terms into this equation. And again, I know this equation looks scary, but we're going to walk through exactly how we solve for our unknown here. So 760 torr and 115 torr. Now, you might think, do I need to convert this to atmospheres here? But when you have 2 different pressures, As long as they're in the same units, those units are going to cancel and it doesn't matter. It wouldn't be wrong if you converted this into atmospheres, but again, you'd be doing the same manipulation for both of these terms. You'd be taking and dividing them by 760. So in this case, you wouldn't have to do any conversion there. We already talked about the need to do a conversion here. I'm just going to do this in my head and make this 40,500 joules per mole, and then we've got 8.314 joules per mole Kelvin. And unlike we had in sample problem 12.1, where we really didn't need to worry about Celsius to Kelvin conversion, in this case we do. Even though we are taking a difference of these, we're taking a difference of the inverse. And so that's going to be very different. So we do need to have temperatures here in Kelvin. So remember to convert temperatures to Kelvin. We add 273, so this is going to give us 308 Kelvin. We need to keep T2 first, and that's what we're solving for. And then we're going to have 1 over 308 Kelvin. Okay, now again, this is the part where you want to make sure that you're getting the right pieces of information from your calculator. Make sure that you use the ln function, not the log or the log function, because they're based on different base units. And so you'll get the wrong answer if you try to take the log of base 10 with this. You need to use the ln. So taking the ln of 760 minus 115 will give you 1.888. Taking and dividing these two numbers gives you negative 4.87 times 10 to the third. 1 over T2, again, that's our variable, what we're trying to find. And 1 divided by 308 gives us 3.247 times 10 to the minus third. Now I'm going to walk through fairly slowly how the algebra works to kind of solve for our unknown here. But that's a really important skill to have in Gen Chem here. We're going to have lots of equations where we'll have to solve for an unknown, and it's just basically some algebra to be able to isolate this variable and solve for what we want. So the best way to isolate this variable is to first divide both sides by minus 4.87 times 10 to the third. Doing that on the left side will give us minus 3.87679 times 10 to the minus fourth. You'll notice here I'm having lots of significant digits that I leave here. That's okay as you work through a problem. It's fine to have lots of significant digits. We'll round at the end, but this ensures that I'm not going to lose some accuracy because I round too early. Again, this is going to be 1 here, so that gets rid of this term. So we're left then with 1 over T2 minus 3.247 times 10 to the third. Again, just working to isolate this variable by itself, we can add 3.247 times 10 to the minus third to both sides. So I'm not going to write that out, but adding 3.247 times 10 to the minus third to minus 3.87 or 3.87679 times 10 to the minus fourth, that's going to give us 2.85932 times 10 to the minus third, and that's equal to 1 over T2. Again, remembering when you're solving and doing some algebra, as long as you do the same thing to both sides of the equation, you're safe. So what we're going to do to be able to isolate T2 by itself is we basically need to take both sides of the equation and invert them. Okay, and that's what this means. When you say something to the minus 1 power, that means you're taking the inverse of it. So 1 over T2 equals T2. And again, we're going to take 1 over this number in our calculator. Speaking of calculators, just to kind of point out, see if you have these buttons that you can easily identify. The 1 over x button. Again, here's the difference between natural log and log. So this 1 over x button, if you just push that when you have this number in your calculator, you'll get 349.7 Kelvin equals T2. The problem asks for calculating the temperature in centigrade. So again, if this was a problem on a test and you circled and boxed this answer, you'd get close to full credit because everything that you had was correct, but make sure to answer the problem how it asks. So in this case, we have to subtract 273 to get our answer in centigrade, and we get 77 degrees C. Now, I always think it's a good idea if you can try to ballpark an answer before you start working on a problem. So in this case, it says to calculate the vapor pressure of ethanol, or the vapor pressure at 760 torr, calculate the temperature when the vapor pressure of ethanol will be 760. Now remember, the magic of having the vapor pressure of a substance be 760 torr is that's going to be the temperature at which the substance boils. So in this case, this is telling us that we would predict that ethanol would boil at 77 degrees Celsius. Well, the actual boiling point for ethanol is 78 degrees Celsius, so that is consistent. So we always want to think about having some way to check our answer. Does our answer make sense? And so always try to think if there's some way that you can make sense out of this number and see if it's in a ballpark that you'd expect.